Today we're going to look at Chapter 3, Part 1, Nodal and loop analysis techniques. So both nodal and loop analysis are systematic approaches to perform circuit analysis. And this week we're going to look at a nodal analysis, and the next week will be a loop analysis. So what is a nodal analysis? Nodal analysis is one of the systematic ways to determine voltages and currents in the circuit. And the variables used to describe the circuit will be nodal voltages. The nodal voltages are the voltages of each node with respect to a pre-selected reference node. Let's look into that by referring to an example that we did together in Chapter 2. So in that problem, you were asked to find all the currents and voltages in this network. So the way that we solved the problem was through the simplification of the circuit network by using the resistors in parallel, in series, and then potentially also delta Y transformations. So what we did here is that we simplified the network step by step. This is the first portion that we simplified this network to be one resistor. Then we put it back into the network, it becomes something like this. By doing this, we lost track of VC. So in this new circuit diagram, there's no longer VC. So, but the VB is the same VB in the previous network, and VA, I1, I3, they're all the same as what we had from the original network. The next step, we further simplified it until we have a very simplified network that will allow us to calculate the current and the voltage pretty straightforward. So we can find the VA by using the voltage division result, and we can find I1 by using Ohm's law. Go through the simplification allow us to solve some of the unknowns in the problem. At the same time, we lost some information from the original circuit. So this is why we need to backtrack. So we solve it backwards by using what we already got. By giving VA, we can find a VB, then we can further find I3, then we go backward to find I5, I4, and also VC. So this is the process of how we solve the problem from using the knowledge learned from Chapter 2. So today we're going to look at a more systematic way to solve the same problem. By looking at the problem, we notice that there are 5 different nodes in the problem. So let's count the nodes together. This is 1 node, 2 node, 3 nodes, 4, 5. So these are the 5, not these 5 dots. So that's a place that you need to pay attention to. This is 1 node, and there's another node over there, although we don't have a dot. So there are 5 nodes in the problem, and if 1 node is a selected reference, there will be 4 voltages with respect to the reference node. For example, I select this node as reference, and this will be one node that has the nodal voltage of this point with respect to the reference. We already know that the voltage difference between this node and the reference that is given 12 volts. So we know that this node has a nodal voltage of 12 volts. Because VA is defined as the voltage between these 2 nodes, and if we pick this node as reference, and this node will have a nodal voltage of VA. Similarly, this node has nodal voltage of VB, and this node has a nodal voltage of VC. So there's a theorem that will guarantee that if we know all these nodal voltages, we will be able to find everything in the circuit. We will demonstrate that by looking at this example. So in this example, assume the nodal voltage of this node M is known. So that is Vm, V sub M. The nodal voltage for this node N that is also known, which is Vn. Given that, we'll be able to find the voltage drop on this R by using the VR is equal to Vm minus Vn. All these nodal voltages are compared to this node reference. We can find the same answer by using KVL as well. If we define a loop over here, so the voltage of VR plus another voltage of Vn. So this is the same node, then plus another voltage drop, which is a negative Vm, that is equal to 0. we can find the same answer. VR is equal to Vm minus Vn. You can find VR by using definition as well. So VR is the voltage drop from this node to that node. You can follow this path. Say Vm, then minus Vn. So you can find the conclusion in either way. So we know that we can find the voltage of this resistor. And by using Ohm's law, we can find the current going through the resistor as well. So now we see that giving all the nodal voltages, we'll be able to find all the voltage and the current in the circuit network. The next question you might have is, how do we define the reference node? Which node I'm going to pick? Defining the reference node is vital. Without the reference node, all the nodal voltages are meaningless. For example, the V1 is equal to 4 volts means that this node compared to this node, or the voltage difference between this node and the reference node, that is equal to 4 volts. And similarly, for V2, giving this node 3 as a reference node, we'll know the voltage on R3 that is equal to 2 volts if we define the reference polarity like this. Given that, we can find the voltage difference between node 1 and 2, which is also the voltage drop on this R2 resistor. We can find that by using V1 minus V2, which is equal to 6 volts. The strategy for nodal analysis. The first step is to identify all the nodes and select a reference node. In this problem, we're going to select this reference node, then I will label all the other nodal voltages. At the same time, I don't want you to define too many variables. For example, this variable over here, we're going to make use of what's already given in the problem. I will label the nodal voltage 12 volts directly over here. And similarly, since this VA is already given, if we pick this node as reference, and we can call this nodal voltage VA. And similarly, this is the VB, and this is called VC. So we maximize the utilization of the variables given in the problem to label all the nodal voltages. So the second step is to identify the known nodal voltages. So we already did that. We can combine the first two steps together. And then the next step is at each node to write a KCL equation. So the next step is to replace all the current in terms of nodal voltages and get the algebraic equation in nodal voltages. For example, at a node VA, to write the KCL equation, if we use I1, I2, and I3, we'll write the equation of a negative I1 plus I2 plus I3 that is equal to 0. Then we can replace this current I1, I2, and I3 by using Ohm's law. I1 is over here. That can be calculated by using Ohm's law of a voltage difference between the two. So Vs minus Va divided by 9, that is my I1. And I2 is similar, we use Va minus 0, because reference that is like something that we are comparing towards. So this is 0. So Va minus 0, so that is Va divided by 6. And the next I3 is Va minus Vb divided by 3. And similarly, we can write a nodal equation at this node Vb. Test all the current by using Ohm's law. Similarly for Vc, we do the same thing. Then we'll be able to solve all these three equations for the three unknowns from the problem. By getting all the nodal voltages, we'll be able to solve anything else from the problem. I6 is the current leaving the node Vc. You can add it back to your circuit over here. Now you are wondering how to write a KCL equation, because there are different ways that you can define your reference direction for the current. So it doesn't matter how you define the direction of the current, they are equivalent. Over here, these two are the same circuit, but I have two different definitions of the current. In this case, I define the current in this way. If I write the nodal equation as the summation of the current leaving the node is equal to 0, then I will have negative I1 plus I2 plus I3 that is equal to 0. And we can replace I1, I2, I3 by using Ohm's law. So that is how we calculate I1, I2, I3. So we replace and put it over here. And further, if we write it as the current into the node is equal to 0, then it becomes I1 minus I2 because it's leaving minus I3 that is equal to 0. And we can replace I1, I2, I3 by using Ohm's law. So if we compare these two, they are equivalent. So if you add a negative sign to the first equation, you will get the second one. So it tells us that if you write the current leaving the node is 0 or write it as a current into the node is equal to 0, doesn't matter. So in the second case, I want to define my current in a different way. Just assume that I define my current in this way. Similarly, I can write the nodal equation by following the summation of all the current leaving is equal to 0. So the equation will be I1 leaving plus I2 leaving plus I2. I3 goes into the node minus I3 that equal to 0. And we replace I1 prime, I2 prime, I3 prime, which will give us this equation. By comparing this equation with the equation on the left, we notice that they are identical. So look, so this is a plus, this term is exactly the same, and this term is the same if we factor this minus sign into consideration. And the first term is also the same because we moved the minus sign to the numerator so that it becomes VB minus VA, right? So the two equations are equivalent. Similarly, we can also write it as the summation of current goes into the node as 0. So we write it as a negative I1, negative I2, and positive I3 that is equal to 0. So we replace all the current by using Ohm's law. We find another equivalent expression. So it tells us that no matter how you define your reference direction for all the currents, it doesn't affect the equation. So you should get the equivalent equation and the final answer should be the same. Now you know that we have many different ways to define the reference current direction. Sometimes it may make you feel confused. So that's why we may want to just assume your own convention to follow. For example, I would prefer to write the equation as the current leaving the node as up to 0. And I won't define all these reference currents. But every time we write the current equation, I use the current node minus the rest of the nodes. So for example, I will use VB minus VA divided by R1 plus VB minus VC divided by R3 plus VB minus VD divided by R2 that is equal to 0. So if you follow this convention, it will help you to avoid a lot of mistakes. And we also learned from chapter 2, the Ohm's law have two different forms. You can write it using resistance, or you can also write it in the form of by using conductance. The conductance form, Ohm's law tells us that current I is equal to the conductance times voltage. Let's look at this example. If we use the conductance to write the equation, in this example we select this node, node 3 as the reference node. Then we label all the nodal voltages, V1 and V2. Given that, we'll be able to write the nodal equation, right? For the first node, we write the equation as, if we follow the convention that I mentioned, I will write the equation as negative IA, because I'm counting the current leaving the node as a positive. So plus V1 divided by R1 plus V1 minus V2 divided by R2, that is equal to 0. So that is how I'm going to write the first equation. For the second node, I'm going to do something similar. If I write that equation, it will become IB plus V2 minus V1 divided by R2 plus V2 divided by R3 is equal to 0. And similarly, we can write the equation by using the conductance instead of resistance. If I do that, I will write the first equation over here, the current leaving the node minus IA, the current in this branch, that'll be equal to G1 times V1. The current in this branch will be G2 times V1 minus V2, that is equal to 0. And we can do the same thing for the second node. which will give us G2 times V2 minus V1 plus IB plus G3 times V2 that is equal to 0. So if we combine the two together, the two equations have this form. We have two unknowns, which is V1 and V2, V1 and V2. And we put all the given currents to the right hand side. And we can see that a coefficient for V1, that is simply the summation of the conductance connected to node V1. So we have two resistors, R1 and R2, connected over there. So the coefficient becomes G1 plus G2. And similarly, in the second equation, the coefficient for V2, that is a summation of all the conductance of all these resistors directly connected to V2. So that is the G2 plus G3. If we look at the cross terms, so the coefficient for V2 in the first equation, that is negative G2. And if we look at the coefficient for V1 in the second equation, it's also negative G2. If we look at the circuit diagram again, we notice that the coefficient for those two terms is the conductance of the resistor shared between the two nodes with a negative sign.
Professor, I have a quick question.
Yes.
How do you get negative G2 with V1?
These two equations come from here. So simply I just put IA to the right hand side, and the coefficient for G1, that is the G1 plus G2, right? So this will have a G1 terms. And the second term is over here, negative G2 times V2, which is here.
Okay, yeah, I see.
So now, given these two equations, we notice that we can write it in a matrix form. We learned that giving you a linear equation set, you will be able to write it in the matrix form. So this will be the matrix form. We put unknowns over here, so these are something that we are looking for. And all their coefficients will form a matrix. And on the right hand side will be the rest of the information. So in this problem, the two currents will be on the right hand side. It will be put into a vector form. This first entity over here, that will be the coefficient for V1. And the second entity over here, that will be the coefficient for V2 in the first equation. And similarly, this will be the coefficient for V1 in the second equation, because this is the second row. And this will be the coefficient for V2 in the second equation, which is over there. The right hand side will be the current that goes into the node. Following the convention, when we write the node equation, we count all the current leaving the node as positive, because we move it to the right hand side of the equation. So it becomes the current into the node. So the current goes into the node V1, that is IA. So this is why we have IA over here. The current goes into the second node, which is a negative IB. This is why we have a negative IB. And the coefficient for the diagonal entities are simply the summation of the conductance of all the resistors connected to those nodes. There are two resistors connected to node V1, which is R1 and R2. This is why we have G1 plus G2. Similarly, there are two resistors connected to node V2. We have R2 and R3. This is why we have G2 and plus G3. And the off-diagonal entities are the shared resistors in between. Between V1 and V2, they share one resistor. And this is why we have a G2 with a negative sign. G2 with a negative sign. Don't forget the negative sign for the off-diagonal entities. So this is also called a model by inspection. So let's look at one more example about how do we model by inspection. And a model by inspection only works for circuits with independent current sources, like this one. In this problem, we have two independent power sources, and both of them are current sources. So we know that we can do model by inspection. If I define this node as reference node, I will label all the other nodes. I will label this node V1, and I'll label this node V2. Remember, this 2 is one node, so don't label them as two different nodes. There's another node V3 over there. So I labeled all the nodes actually, right? There are only 4 different nodes in the problem, because I selected one the reference node, I only have the other three. So in this problem, I have three unknowns. If I can solve these three nodal voltages, then I will be able to solve anything in the circuit, no matter what you ask me, and I will be able to tell you. So I will start writing the equation. First, I will put the unknowns in a vector form. So I have V1, V2, V3, and on the right-hand side will be the current goes into the node V1, node V2, and node V3. Let's see. So the current goes into the node V1, that is a negative IA because it's leaving, right? The current goes into node V2 over here, which is a negative IB. Remember, this is also the current that goes into the node, right? So this is why we have a IA minus IB. There's no current source directly connected to V3, so this is why this is 0. Then we'll look at the matrix. This is the most important part for us to get the equation. So we'll write down the diagonal entities first. So we know that the diagonal entities are simply the summation of the conductance of all the resistors connected to the corresponding nodes. So this entity over here that represents the summation of the conductance of all the resistors connected to node V1, and this is about those resistors connected to node V2, and this over here that is the resistor related to V3. There are two resistors directly connected to node V1. So we know that this entity will be 1 over R1 plus 1 over R2. And for node V2, there are two resistors directly connected to node V2, which is R3 and R4. So this is why we have 1 over R3 plus 1 over R4. For node V3, there are three resistors directly connected to V3. So this is why we have 1 over R1 plus 1 over R4 plus 1 over R5. So now we got all these three. The off-diagonal entities are the ones shared by different nodes. So this is the first row, second column. So this one represents the shared resistors between node 1 and node 2. And this entity over here, that is the first row, third column, it represents the shared resistor between node 1 and 3. So let's look at that. Between node 1 and node 2, there's no shared branch with a resistor. So this is why we have a 0. And between 1 and 3, there is one branch with a shared resistor. This R1 is connected both V1 and V3. This is why we have negative 1 over R1. This matrix is symmetric because this entity is between 1 and 2, that is the same between 2 and 1. This entity is about the shared conductance between 1 and 3, and this is between 3 and 1. So this is why when we get to the first row, we got the first column. This matrix is symmetric. And the only entity left over that is between 2 and 3. The second row, third column, and the third row, second column, they are the same. Between node 2 and node 3, there is one shared branch. This resistor R4 is connected to both node 2 and node 3. This is why we have negative 1 over R4. So this is how we write the nodal equation directly by just looking at the circuit diagram. And then we can briefly mention about the property of the matrix. And we know it's always symmetric. And the diagonal entities are always positive because that is the summation of all the conductance of all the resistors. And off-diagonal elements are always negative. So this model by inspection only works for circuits with independent current sources. So we kind of talk about a special case where we can do model by inspection, and now we're going to talk about a general approach. So what if a problem that is not like what we discussed before? It might have a dependent power sources, it might have voltage sources, and how do we solve problems like those? If we have a circuit with dependent sources, we cannot model by inspection, but we will write the nodal equations by treating all the dependent sources as regular sources. And once we do that, you know that we introduce new variables, and these new variables are called controlling variables. This control variable tells you what is the voltage for the dependent voltage source, or what is the current for dependent current source, it implies that we will need additional equations. And this additional equation will be about this controlling variable. And we need to write this controlling variable in terms of nodal voltages so that we only introduce new unknowns. Make sense? Because we define all these nodal voltages will be the unknowns. We don't want to introduce more unknowns. So this is why we need to find a relationship between the controlling variables and the nodal voltages. Or you can say we write the control variables in terms of nodal voltages. Let's look at one example. So in this example, we have one current source, nice. Another current source, nice. But this is a dependent current source. And this current source depends on another current, which is I/O over there. So when I write the nodal equations, I will first treat this as a regular current source. I will be able to write the nodal equation about these two nodes. I will select this node as reference node. For the first node, I will write my nodal equation, say the current leaving the node, which is beta I/O, the current leaving this node, which is V1 divided by R1, the current leaving this node in this branch, that is V1 minus V2 divided by R2. For the second node, we'll be able to do the same thing. The current leaving the node in this branch, that is V2 minus V1 divided by R2. The current leaving this node in this branch, that is V2 minus 0 divided by R3. You can neglect 0, you just write it as V2 divided by R3. The current leaving this node in this branch, that is negative IA. So this is how I find my nodal equations. Then the problem is I have three unknowns. There is additional unknown, which is I/O. I/O is called a controlling variable. So I need an additional equation. This additional equation is about writing I/O in terms of the nodal voltages. We find I/O is over here. And I/O can be found by using Ohm's law, by using the nodal voltage V2. So we know that I/O is equal to V2 minus 0 divided by R3. So this is how we find the third equation. Now we have three unknowns, V1, V2, and I/O, and we have three independent equations. Then we'll be able to solve them. So that is how we solve the problems with dependent sources.